Hi, my name is Jin. In this video, I'm going to show you my machine learning program using blackjack. I don't know much about the machine learning standard thing, so this program might look a bit weird, but hopefully you enjoy this video. Basically, this is the blackjack game, so I try to figure out and apply the most common rule for blackjack. And there's a lot of different rules, a lot of different variations for blackjack. So I had to surf the internet and check the website of casino, and it turns out, as you can see here, I applied the 6 options for player, and you can check the other detail rules on the bottom. And some rules might not be that super common, like surrender, re-split allowed, double down after split allowed, but it's still acceptable, and I just wanted my program to be more flexible with more possibilities for whatever it is later, so I just applied it. The most famous well-known strategy in blackjack, the card counting. Here's a short explanation here. It's all about expecting the advantage of current deck based on the cards which were used so far. Later I will take how I apply this with actual codes, but simply explaining first, I divide the database by card counting number, and AI keeps calculating card counting number and use it to either read or write the data. So I set the card counting range from -20 to 20, which covers pretty much all the cases that we might encounter in real game as well as simulation. I'm gonna show the program very quick. Now we are in playing mode. We can just play the game and get a card. I'm gonna go hit here. Okay, I got first and I lost my bet. And we can play another game. Here I will do insurance and go hit again.
Player busts.
So it's just same as normal
Maybe next time.
game, but this game doesn't affect anything on learning process. Instead, in the background, the AI keeps simulating games for learning separately. So even right now, the AI is doing its work. This is the chart room. Here we can check the databases that AI collected so far. So this x-axis means the index of dealer's open cards, and this y-axis means the index of player's first hand. So it covers from hard hand, soft hand, and double hand. So all of this is a result of after about 13 hours of learning, and all this situation is showing their first choice recommendation when you just have your first hand. So these choices is gonna be their best winning choice or least losing choice. If you click it, you can check the detail of it. Here, this is the databases that collected for this situation when the dealer's open card is ace and your hand is double three. That's a hit, stand, double down, split, insurance, surrender. So this first number here before slash means the trial number. How many times the AI choose the hit in this situation. And this second number is the actual win rate from this trial number. So this means you're gonna lose about -0.32, so about 32% of your original bets if you play the game in average. Here, the best choice is the H, the hit, so it's showing H here. And you can check another case. Here, your hand is not a double, so you can't split. And dealer's open card is not an ace, so you can't insurance as well. So it's showing just rest option. And here, the hit is the best choice, so it's showing H. And this is the card counting number that apply for these situations. So the recommendation choices from this situation only apply for this when this card counting number is the 0. And you can go next and check another recommendations for different card counting number. So each card counting number have their own specific recommendation choices. So as you going next, you can see it changed gradually. So it get more stand and get more surrender. Okay, we go to 20. So here is the end of the range, and you can also check the detail of it. So, and if you compare the recommendation choices between 20 and -20, then you can see the obvious differences here. And here, and here. And this is actual code of our database by XML. This first element, we're gonna take it later. And this here, it has all elements that covering the index of dealer's open card, so from 1 to 10. And if you go one of this, you can see so that each dealer hand, this element have all index of player's first hand, so from hard hand, soft hand, and double hand. And if you go one of them, you can see, yeah, each situation have their own data about these different options. So as we checked earlier, this first one is trial numbers, and this second one is actual winning rate of each option. I wanted to visualize the progress through the generation, so I let the program to play the game automatically with some specific amount of learning data of the generation. So it starts with no data. So here it just keep hitting until it gets 21 or first. So most of the time just lost. In seconds, it play with about 60,000 data. It's not enough, but it know there's another option and it choose another option. And the next, it play with about 1.8 million data. And here it plays pretty well, 11. And I want to speed it up the pace, so I waited for about 13 hours for learning data this time. And the game now are being played. This is the game number so far. It's really quick. And this is the average of overall winning rate. So this, as you can see, just below the zero. It's barely losing its money. The only main theory that my learning process is based on is the law of large numbers. This is the theory of the probability. It states, as you can see here, as the number of trials increases, the actual probability approaches the theoretical probability. I will take the flipping coin example with this chart. Let's say we want to get the probability of flipping head. Here, this x-axis indicates the trial numbers, how many times you flip the coin. And this y-axis indicates the actual probability, 0%, 100%. And right side here, this is pretty obvious. This is the 50%, which is theoretical probability of flipping head. And you start flipping coin. In this early period, you can see it lies from 0% to 100%. You couldn't really find any consistency here, because if you have just few trial numbers, it is possible that you get 100% of head or 100% of tail. But if you're flipping coin over and over again, you can see the lines here getting closer to 50%, which is theoretical probability of flipping coin. And this is cool because you don't have to work out with some mathematic complicating formula things. All you're gonna do is you just try enough times and collect them all and get the average from them, and that's gonna be the answer. This is the learning process. The first hand just dealt, and here's the options for the AI. You can think each of these options as same as flipping coin. The result of whether you win or lose gonna be stored in its corresponding database. So during the learning process, the AI admit a lot of different situations defined by the dealer's open card and the AI's first hand. So the AI would choose the random option for the first choice and collect the result. I will take one of the first option stand as the example. As you can see here, the database contains two numbers. The first one is the trial numbers. How many times AI choose the stand in the specific same situation. And second one is the actual winning rate from these trials. So 0 means you lose nothing. You just save your original bet. Minus 0.1 means you're gonna lose 10% of your original bet, which means if you bet $10, you're gonna lose $1 in average. Let's take two simulations. Let's say AI choose the stand twice, and first time you win. And to combine this new result with this original database, you go through this process. First, you get the sum rate by multiplying trial number by winning rate. It's gonna be minus 1.5, and you add 1 at it because you win the game. This value can be more than 2 because if you double down or if you win multiple hand because you have additional bet. And you divide it by new trial number, which is the original trial number plus 1. And then you're gonna get this new winning rate. Next time you lost, you go through just same way, except in this case you subtract 1 because you lost. And also this value can be less than 2 if you double down or you lose your multiple hands. So after these two simulation, the database, the winning rate, gonna be like this. So as you keep collecting the data, the average in database gonna get closer to the theoretical probability. Let's say these are the databases of some specific situation, and you can see the double down has the best winning rate among these options, which means in this situation double down is the best choice. So in the chart room, this case will be showing D mark for the recommendation. So simply you can just think this is just the process of flipping a lot of different coins. Everything is just flipping different coins, of course collected on its own database. So the total database size would be like this. So this 41 means the card counting range from -20 to 20, and this one is variation of the card. So this 10 is the variation of the dealer's open card, and this 35 is the variation of AI's hand, and this 5 is the first option that we checked earlier. Before going to the code, this is the brief structure of the class. The top here, this is AI controller. This is kind of main class that operate the learning process. So it has all object it needs for simulating. So it has a deck, it has a player, it has a dealer as well. So the deck can have multiple cards in it and pass the cards to the AI hand here, and this player hand, dealer hand inherit from this AI hand. And since the player can have a multiple hand by splitting, so this AI player can have multiple player hand. And of course the dealer have only one hand, so it doesn't need anything else. This is the data manager. It is for database, so it's save the data, load the data, something like that, and another classes here, and etc. I will go through this AI controller class. In this update, there is 2000 time loop, and this one process means one single blackjack game from getting ready to clear table. So after one frame, you're gonna get about 2000 results that's stored in database. Okay, let's check this ready function first. Inside this ready function, this one is important. This is result information structure. Okay, this is this one. This structure contains the information about the one single result. So this is the card counting number just after you get your first hand, and this dealer index indicates the open card of the dealer, and this player index indicates the player's first hand, and this is first choice, and this is this winning rate is actual data that indicates how much you win or lose. So this full variable is kind of address to find out right database to that this actual data should be stored in. So after finishing this ready function, we go into this function. Here we set our first card. So the player get his first hand and dealer get his first hand. Just after the player gets his first hand, we set our result info structure. So okay, card counting number, we store the player index and dealer index. And then before we go into player turn, we check the insurance first. Okay, if the dealer hand is insurance, which means dealer hand is the first hand, and if the open card is the ace, then we can choose the insurance in 20% possibility. And then we go into player turn. Unless the both player and the dealer is blackjack, then we can make the choice. Here we declare the new card choice, and we get the list of the all possible options from our current hand, and then we get the random option from it and store it into this current choice. And if this result info property, the first choice property, is not determined yet, we store this random option data into this first choice as well. So what you mean by that, all choices here, like first choice and extra choice, determined by random. So depends by this current choice, we execute these different options here. The double down, split, surrender, and so on. And also we execute all hands that we have inside this loop. Okay, this was the player turn, and after that we execute dealer turn. This is pretty simple than player one. So unless dealer is the hand of the dealer is more than 17 or equal to 17, and dealer get the burst, the dealer just keep hitting. So after dealer finish his turn, we get into result. The first we calculate the amount of data, amount of the betting. So we can get this winning rate from this betting and store this into this result infrastructure, and then we pass this into database manager. So we can store the result into the right database because this structure has address and actual data, everything. So after this, we just clear the table and played another game. As we checked in the code, all choices including first choice and extra choices are made by random, and this can be a problem. In case of the stand, double down, surrender is fine because you don't need the extra choice for this. Whether you win or lose, you're gonna get the proper result of the first choice. But in case of the hit, splash, insurance, you need extra choice for this. As you can see the examples here. In the hit, you choose between hit or stand, and you can actually hit as much as you want unless you get the burst. And in the split, you get the multiple hands, so you gotta choose extra choices for each hand, and insurance it's the same. So no matter how many extra choices are made for a single result, it is represented only by this first choice, ignoring all this extra choice which affect the result. If the choices are random, the result of the same choice would vary every time without consistency, which means losing the effect of the law of large numbers. And my solution that I found was to choose the best option instead of random for these extra choices. It sounds a bit tricky because, as I said, to get the proper result, you need to choose the best option. And in reverse, to choose the best option, we need to get the proper result. It sounds a bit weird, but just really simply thinking, let's say in insurance, whatever it is, we figure out the hit and we figure out the split. This will figure out the insurance. In same way, in split, if we figure out the hit, this will figure out the split. So what you mean by that, if we figure out how to get the proper result of the hit, then we will be able to get the reliable winning rate of the hit. This will fix all problems. Let's get into the situation that you are playing the game and now you're considering hit or not. And then the three things you will consider in your mind. The first one is a possibility of winning with current hand, which means the actual winning rate of stand, and we can get it in a database. And the second one is a possibility of burst when you have additional card, and we also can get it in the database as well. When we check this database, these elements is 4 choices that we checked earlier, and this very first one has the information about the burst. So during the learning process, whenever AI gets additional card, it calculates the value of current hand and store the data in it, store the result. So it means this try 23,000 times with this 12 value hand and gets 30% of burst, and so on. And it reach up to 91% when you have a 20 value cards. And the last one is the personal game sense. This is from your game experience, and I describe this as just constant rational value in the code. So what you do is you quantify this value and this value and get the average of 2 value, and compare that average by this personal game set, which is just constant value in the code. So you can decide whether you hit or not, which means stand, and this will get you the best choice. Back to the code again, we have to edit the lines of code here to fix our problem. So now all choices are made by random, and as I said earlier, the extra choices should be only the best one. So I'm going to put these 2 lines which makes the random option into the scope so that it only happens when we store the first choice. And in the else, when we store the extra choice, we only have the best choice. We pass the dealer index here. Let's check this function. Inside this function here, we access the database and we pass the address that we want, the situation that we want to get. And then we declare this dictionary and we add all possible options for current hand and its corresponding the winning rate of each option. And inside this dictionary, we compare the winning rate of each option and returns the best one. And now all we have to do is the hit. I already added it. This is the key function. So it operates the process that goes through in your mind when you consider the hit. The three things that I showed you earlier. Let's get into function. So first we get the actual winning rate of the stand. So we access the database, we pass the address for this, and I get the data. And second, we get the possibility of getting hit. And we also access the database again, but in this time we pass the card counting number and only the value of current hand. And then with this two number, we get the average. And for this, we use the hit weight constant. This is kind of giving weight between hit or stand. So if this value is more than 0, then you are more likely to hit instead of stand. And in the last step, you compare this average by this hit preference, which I call game sense in the picture earlier. And this number and this number looks really weird. Like this one is 0.425 and this one is 0.615. I don't know why this number should be like this. I just simulate the game with some amount of learning data. I set a different number into it and I played a lot of time, and it turns out these numbers are giving the best winning rate for my program. So this was the prefer hit function, and then if this is true, then it will go into the loop, so it keeps hitting. And if this is first, then get out of the loop, which means stand. And this is the overview. These three charts are from my program after about 13 hours of learning. And this chart, very left one, is well-known basic strategy that you can easily find on the internet. So if we compare this basic chart from internet with this result, because the card counting number 0 is the most common situation, even though I applied some different rule for my program, you can see it's almost same. And if we compare this recommendation when the 20 and recommendations when the card counting number is -20, you can see the obvious differences between. Here it's showing much more double down and stand and split instead of hit, and here it's showing much more hit instead of another option. Because when the card counting number is -20, it has much low possibility of getting burst. And in my program, I found some interesting result about the advantage of card counting. The most well-known thing in card counting is the higher card counting number, the more advantage you get. So I test this with this test script. It's almost same as AI controller, except it always chooses the best choice and it never learns. So inside this result function, end of the game, I collect the first data when the card counting number is more than 10, and second data when the card counting number is only less than 10. So I get the average of first data and second data, and I print it in the log. Let's check the log here. So when the card counting number is more than 10, which is supposed to be better situation, it's negative value, winning rate is negative value, and if the card counting number is less than 10, it's showing positive value. So this indicates you're gonna earn about 2.8% of your original bet in the game. So this one is just against what I heard from internet, but I just hope this one's correct. This is the end of the video. I will leave the link below so that you can download and play if you want. Thanks for watching.